Today we're going to look at the activation functions we use on the neurons, so those functions that make the transformations nonlinear, and also the loss functions that we use to train the network. So we're going to look at the activation functions both within the hidden layers of the network and also on the output. And we'll see that the loss functions we choose will depend on the output of the network, and also the activation functions that we have inside the network in the hidden layer will play an important part in the efficiency of the optimization when we are training the network. So we're going to start to look at the question of whether we should try to solve problems with wide networks or wide and shallow models, or instead of that, using deep neural networks. We'll see the benefits and problems with each approach. And then we're going to look at the vanishing gradients problem, which is a problem that arises with some activation functions when we are dealing with deep neural networks. We're going to see how rectified linear units can help us solve this problem, and then we'll look at the different activations, when to use them, how, and how they impact the loss functions. So let's start with this question. There is this universal approximation theorem that tells us that if we have one function that is non-constant, bounded, and continuous, for example, the sigmoid activation function, and we have a boundary, a space where we have some other continuous function. So this is, we can imagine a cube of dimension 1. This is an arbitrary dimension, but this is a multidimensional cube with any number of directions that we want. And we have some function f that is continuous in this volume. And for some error boundary, we can prove that we can adjust n constants of this type, v, w, and b. So this is a weight given to each instance of this function, for example, the sigmoid activation. And this will be a linear combination of the input vector in this space. And we can adjust these parameters, if we have enough of them, so that the difference between our estimate and the actual function we are trying to approximate is always below this epsilon. So no matter how small the epsilon is, we can, by using a sufficient number of neurons, this was proven for sigmoid activation, but this is a more generic result. If we have a sufficient number of neurons, then all we need is a linear combination of those neurons, and we can approximate any function within some finite domain. So this means that a neural network with a single hidden layer, note that we need to have a linear combination of the neurons, so it's like we have a hidden layer with an arbitrary number of neurons, and then we just add everything together and output a linear combination of that. So with a neural network with a single hidden layer, we can arbitrarily approximate any function within a finite domain. So in theory, we could solve all problems with a single hidden layer. The thing is that we need some number of neurons that depends on how close the approximation we want to be. So how large or small this epsilon is. But in general, one layer can, in theory, approximate any function within a bounded region. So the question is, why are we using more layers? And one simple answer for this is that if we add layers, instead of just having one very large layer and simply computing a linear combination of those neurons, when we stack neurons and each layer transforms the output of the previous layers, we can have a greater oscillation, larger oscillations in the output of the network, that is the activation at the end of the network, with fewer neurons overall in the network. And these oscillations, so the ability to change from one value to a different value very quickly with small changes in the input, these oscillations are related to the Vapnik-Chervonenkis dimension. So this, just to recall, we saw this last semester, but we say that the hypothesis class shatters a set of points if for any labeling of that set of points there is a hypothesis in this hypothesis class that is consistent with that labeling. That is, it classifies without errors. So suppose we have 3 points in 2 dimensions. Of course, if all points are the same color, then this is a trivial problem. If they are of different labels, any combination of labels that we choose, we can use a straight line to separate these 3 points. So if we have these 3 points, we can separate them, classify without errors using a straight line, regardless of the combinations of labels that we choose. So we can say that the hypothesis class composed of all straight lines can shatter this set of 3 points in this way in a triangle. And the VC dimension is the largest the largest number of points for which we can shatter with a given hypothesis class. So for example, if we have 4 points, then we cannot find a way of placing the 4 points such that for any label, any labeling scheme, we can separate with a straight line. There are some combinations of labels we will not be able to separate. So a straight line in 2 dimensions has a VC dimension of 3, because that is the largest number of points we can shatter. Now, if we have a deeper neural network, we have larger, it's easier to get those oscillations, so you have more oscillations, and we have a larger shattering power. There are larger sets of points that we can classify without errors, regardless of the labeling, with fewer neurons. So the big difference here is that this approximation with one hidden layer, in theory, we can have an arbitrary approximation to any function if we have enough neurons, but if we stack the layers, we can do that, for example, for classification with fewer neurons. So that is one big advantage of using deeper networks. Now, we also saw this no free lunch theorem in passage in the first lecture, but the idea is that for any 2 learning algorithms, in theory, we can find just as many situations in which algorithm A is better than B than the situations where algorithm B is better than A. So there is no learning algorithm that is simply better than any other for all possible situations. Now, this is a theoretical result that can be proven, but assuming any possible distribution of data, that is, any logical distribution of data that could in theory be possible. But in real life, we don't have all possibilities that would be logically allowed or mathematically allowed, and the data is constrained by how reality allows it to be. So in practice, there is, for any given problem, usually algorithms that work better and others that do not work as well. So in theory, there is no single algorithm that can solve everything equally well, but there is, for each particular problem, algorithms that are better or worse. So here, sometimes we need to choose if we want to use simpler models or shallower models, or if we want to use deep learning. In this course, we are focusing on deep learning because of the advantages we're going to see a bit in more detail later on. But you should not take it on faith or blindly choose always deep learning, regardless of what the problems you're trying to solve. So I'm going to give you an example of that. But basically, if we have very simple models or shallow models, for example, linear models or something like that, we have some advantages, which are, for once, we can we have a model that is better at memorizing some interactions of features, even if they occur a few times. and they are easier to interpret, because if you have something like a linear model, you can say that each feature has a particular weight, and you can understand how after training the model your classifier is looking at the different features. One problem here is that we usually need to engineer the features adequately. For example, in recommendation systems, where you go to buy something online and you have a recommendation because customers who purchased what you are buying also bought something this or other. So this you can easily, with a simple model, find all those examples where customers bought exactly the same pair of items. However, it's very difficult to generalize. For example, if someone bought a song by this author, if they will like other songs by the same author or something like that. In that case, you need to engineer the features so that the model also includes their information about the author, or is aggregating all the songs by the authors or something like that. Because the model itself, without that feature engineering, will not be able to find those relations. However, when we go to deep learning models, we can solve those kinds of problems because with deep learning, we have all those different representations of the data in our hidden layers. So the model is transforming the data, and it's much better at generalizing by identifying relevant features automatically without our intervention. So, and this is especially useful if you're dealing with unstructured data, because with unstructured data, it is very hard to do feature engineering manually. However, these models have this property of being very difficult to understand. We cannot pinpoint exactly why they are doing those decisions. And this is an example of some tests done on image classification models, and even for ourselves, for our own biological neural networks, where we have, for example, here images of dogs and cookies, and images of dogs and mops, or bagels and these other dogs. And the classification algorithms can make mistakes with these images, as well as humans, because these things look very similar when we look at them. But we cannot really say what is going what are the actual features that are being mistaken, or interpret this. We know that we can make confusion between the different types of images, but we cannot really point to a specific feature or explain that confusion in some explicit manner. So this is a problem. The interpretability problem of these deep neural networks is one issue that arises when we prefer these models. But let's see an example. This is an interesting paper from Google, which is for recommending in an app store. The algorithm is recommending purchases to the users. So it needs to model that people, when they buy some things, they also buy these other things. So that increases the probability that they want these other types of apps, for example, or products in general. But there are two issues here. One is looking at the exact pairs of what people bought, and the other is trying to generalize from the kinds of things that they are buying. And wide, shallow models like a logistic regression is good on the first task of really matching things in detail that people are buying together, whereas deep models that are narrower but have more stacks, more layers, tend to be better at the generalization, but not so good at actually memorizing those particular correlations. So what these authors did was to join the two together. And so the shallow model, the logistic regression, could find things like this, that people, for example, who brought fried chicken also had a higher probability of then buying, for example, chicken and waffles, but it could not relate that chicken was also something that appeared in chicken fried rice, for example, because these were just different products, and this model was not creating some representation, some embedding these vectors where these similarities could appear. So we cannot get a model like this, like a logistic regression, to generalize from categories unless we explicitly give it the categories. That is, if we create additional labels that the model can use. But deep models work differently. When we have this very large vector of all the purchases, of all possible purchases, then the deep network will create more dense representations with fewer dimensions. And in these vectors, which are called the embeddings, we can find proximity between different items because they tend to occur in some relation with other similar items and things like that. For example, it could be that in the embedding we have fried chicken and hamburger close together, so they seem to be mostly the same thing, even if we do not have explicitly pairs of those being bought together by the same person. So what the authors found was that if they used the two models together, they tested this for 3 weeks on 1% of the customers. This is a typical way of testing innovation in these kinds of online services, where you can take a small sample of the customers. You use one sample for control group, another where you apply the model, and so on, and then you measure the impact of your changes. So what they found is that combining the two models, so this wide model is a logistic regression, which basically is a linear model on all the purchases that can be done, and combining this with a deep model, a deep neural network, they could increase nearly 4% the sales of this app store relative to what they had before, which was just a logistic regression model. But if they only used the deep model, they had a bit less performance increase, so only 2.9% increase. Now, this may not seem a lot, but since they have 1 billion active users at the time, possibly more now, then just a few percent more sales can actually mean a lot of money. So the message here that I wanted to convey is that although we are focusing on this course on deep learning, because these deep models tend to create these representations, these internal representations of the data, which makes it easier to use the data without manual engineering, is very good for unstructured data, and can find more complex relations between the examples. They also have some disadvantages on interpretability, for example, understanding what the model is doing, or even in identifying simple relations between specific types of examples. Because when our neural networks create those internal representations, we are stacking layers of neurons that tend to be narrow with respect to the input, to the dimensionality of the input vectors. So we must squeeze everything, so to speak, into a lower dimensional representation, and this may lose some details about specific correlations. So basically, remember that there is no magical bullet, no model that can solve any problem better than all the others. And even though we are focusing on deep learning in this course because of these advantages, especially with dealing with unstructured data, keep in mind that there are other models that may be more appropriate in different situations, or even a combination of deep and shallow models. So let's see now a problem that arises when we decide to use deep models, because when we use deep models, deep neural networks, we need to train them by propagating the derivatives, the gradient of the error, over many layers so that we can reach all the parameters that we're trying to adjust. So we saw this in backpropagation. In order to update a weight on the output neuron, we need to chain the derivatives of the error function with respect to the output of the neuron, the output, the result of the activation function with respect to that weighted sum of all the inputs, and then this weighted sum with respect to the weight, the particular weight that we're trying to update. Okay, so here we are multiplying three derivatives, and if we go back along the network, we have to do this for all the layers, and we keep all these multiplications, so that the further back we go along the network, the more of these multiplications we have, because we have to back propagate the gradient of the error all the way from the output of the network to all the weights we want to update. Now, one thing that can happen is that some functions, for example, the sigmoid function in the logistic activation, or the hyperbolic tangent and things like that, they can saturate. So there are some values where the derivative of the function starts to approximate zero. And if this happens, if anything here approximates zero, since we are multiplying them all in a chain, now everything vanishes. Because you multiply by zero and it all goes down to zero and you lose information. So when this happens, we cannot train the network. All the gradients will be zero with respect to a lot of the weights, and the weights simply will not change anymore. So you can actually try this using the TensorFlow playground, the one I showed you in the first lecture. If you want to go there, you can experiment a bit. So if we use sigmoid activation and use this data set that has this orange and blue separating this way, we can use a single hidden layer to solve this problem, and everything works fine. So with 370 epochs, we already have a good classifier. If we use this more difficult problem where we have these spirals, then with a single hidden layer with 8 neurons, we cannot get it to work. So maybe in theory, if we had enough neurons, then this should work. If we increased the size of this layer due to that theorem of the approximation, but we would probably need a very large number of neurons. And the problem with that is then if you use very, very large numbers of neurons, you will tend to overfit a lot, even if you have a lot of data, and the problem and the model will not perform as well. So what we can do is to stack neurons to make these to compose these different transformations. So the first layer will transform in one way, then the second, then the third, and then in the output we could have a better result. But after 1,400 epochs, we still are not able to properly classify these data. And if we increase even more the depth, we still have this problem. So it seems to have made a bit of a difference there, but there's still a lot of errors here, even after 2,000 epochs. So the problem here is that when we stack these layers with the sigmoid activation, we start getting this vanishing gradients problem, where all we need is for the derivative at some point to be close to zero, and then the gradient will disappear and we lose information about how to update the weights. And this happens with the sigmoid activation because if we go away from zero, from the center here, so at this point the derivative is large, but then if we approximate higher values or lower values, then you see the gradient here, the inclination of this line is tending towards zero. On both extremes. So as we start to saturate the activation, we lose the gradients and everything stops. So this is one thing that we can solve with the rectified linear unit. And this was really a big innovation that allowed the training in practice of deep neural networks. So the sigmoid activation we saw, the formula is this one, and it saturates here on the higher values and lower values. There are variants of this. For example, the hyperbolic tangent has the same problem. It's similar to the sigmoid, but it varies from -1 to 1 instead of from 0 to 1, but it's still the same kind of curve. And as we approach higher values or very low values, the derivative also tends to 0. And anything that has a derivative at 0 will then, when we multiply the gradients in backpropagation, make everything go to 0, so we can no longer train the network in those conditions. The rectified linear unit is a lot simpler than the others. It's just that if the input value is below 0, we have a 0 on the output. So this is constant like this. If the input value is greater than 0, then we simply output the input value. Now this is seems like a strange activation function. It does not simulate what the biological neuron does or something like that. But mathematically it's much simpler, computationally it's much faster to evaluate, and has the advantage that as long as the neuron is firing, the derivative is always 1. It's a constant derivative, regardless of what the value is. So we always have information on which direction we need to change the weights, and these derivatives do not disappear. They can disappear if the neuron is no longer firing. So in this case, we have a derivative of 0 because in this part it's 0 in this particular version of the ReLU. But this only happens if the neuron is not active. So when the neuron is firing, we do not have a vanishing gradient. And if we use this, it makes a lot of difference. For example, with a sigmoid activation and 3 layers, after nearly 1500 epochs, we still do not have a good result here. But if we just change the activation to a ReLU, it's exactly the same architecture. Now we can separate the two classes easily, even only after 270 epochs. This because when we start saturating the sigmoids, we start having zeros here and training stops. With the rectified linear units, training doesn't stop as long as the neurons are firing. We keep having information about how to change the weights, so we keep improving the network until we solve the problem, and it's much faster. So this is really a very big difference between using sigmoid or hyperbolic tangent or that sort of activations in the hidden layers, or using rectified linear units. And you can even stack more layers and it doesn't matter because it still works. It doesn't suffer from that vanishing gradient problem. So this was really a big innovation in training deep neural networks, and basically the message here is that for hidden neurons you should prefer rectified linear units. If you use sigmoid activation on hidden layers and you stack lots of them, even few of them, you don't need many, 3 or 4, you already start having problems with the vanishing gradients. So advantages of rectified linear units are that it's fast to compute and it does not saturate for positive values. So gradient is always 1 as long as the neuron is firing, and we don't lose the gradients in backpropagation. One problem with rectified linear units is that they can die. Suppose that the weights become very negative and all the examples are falling on this side for a particular neuron. In that case, for all the examples, this particular neuron will never fire. The gradient here is always 0, so this particular neuron will not change its weights anymore. And this, effectively, this neuron has died. It will never fire and never change the weights, and so it's as if it wasn't there anymore. But this is a problem that can be solved with some variants of rectified linear unit, which you'll see right away. So this is the simple, the vanilla version of ReLU, and has this problem that if for all examples one particular neuron is always falling on this side, then it will never change and it will remain dead forever. So this will be irreversible. If for some examples it still fires, then it will have, in some cases, a gradient that is not 0, and the weights can keep changing. So as long as the neuron fires at least for one example in all the training set, it still can remain alive. But if it happens that it doesn't fire for any of those, then it will remain dead forever. One way of solving this is to use a leaky ReLU. So a leaky ReLU is one that has this elbow all the same. Note that if we did not have this elbow, for example, suppose that we have an activation function that was like this, just a straight line, this would not work because we need some non-linearity to stack over the layers in order to obtain something that is not merely a linear combination of the inputs. If we have a linear activation function, then that layer is not doing anything in addition to what any other layer could do just by using linear combinations of the inputs. So we need a non-linear activation for this to work. But all we need is this kind of elbow to make the activation function non-linear. So we can have this leaky ReLU, which the same as the original one. The output is x when the input is greater than 0. But if the input is smaller than 0, then the output is a fraction of the input. So there is this elbow here because the inclinations are not the same, and it's a non-linear transformation. But it doesn't die in the same way that the others do because the gradient will never be 0. Note, by the way, that this is how it's described on the original paper and sometimes in the literature. But when we use the leaky ReLU in TensorFlow, this is actually a value that we multiply by the input. So you should use a value that is smaller than 1. Another version is the parametric ReLU, which is similar to the leaky ReLU, but this parameter here is also learned during training. So we are also adjusting this parameter for the neuron during training. The randomized leaky ReLU is another variant. It's just that the parameter we have here is taken at random in each step of the computation, in each step of training, for example. It's taken at random from a uniform distribution between a lower and upper bound. And then when we finish training for using the network, this parameter will be fixed on the average of this range. So during training, we are picking at random. This may have some effects of similar to regularization, for example. But then after training, we fix on the average value and we use that. So if you want, you can see in this paper from 2015 an empirical evaluation of different ReLUs. Basically, leaky ReLU seems to work fairly well with this kind of, say, 20% on the leakage there. Remember that this alpha here on the paper is what we are dividing this. So if you want to implement this like this on TensorFlow, it should be 1 over this alpha for the parameter to use. But the idea is that leaky ReLUs seem to work a bit better, at least in these examples that the authors used. But in general, if you use just the simple ReLU, it often works well too. So in any case, these are much better than using the sigmoid activation, which will really bog down your training if you have deeper networks and you won't be able to train anything. Then there are other more complex variants. For example, concatenated ReLU combines two ReLUs for the negative part and the positive part. So the output is something like this. And then you have the exponential linear unit, which uses a linear activation here on the positive side, just like the ReLU, but then an exponential curve on the negative side, so that there is no discontinuities in the derivative. So this was also experimented with because intuitively there seems to be a problem when we have this kind of elbow and the derivative is not continuous. However, in practice, the big difference between a standard ReLU and an exponential linear unit is that this one is more expensive to compute, and we don't get a big advantage for this. In any case, there are lots of these activations that you can choose from. In general, in the hidden layers, use something like ReLUs, but if you want to experiment to see in your particular problem something different works better, it's easy, and we'll see how we can do that further on in the course. So now, which activations to use? So basically, on the hidden layers, we just need something that to make the transformation non-linear, and it should be fast and avoid vanishing gradient. So ReLU, especially leaky ReLU, tend to be the recommended choice for hidden layers. There are some exceptions. For example, long short-term memory recurrent networks have very specific activations because they have specific blocks of neurons, and so in these we use those activations and not ReLU. So there are some specific architectures that do not use ReLUs, but in general, if you are just creating your own network, this would be the best choice for the hidden layers. But for the output layers, it now depends on what the problem is that you're trying to solve. So let's see here some 3 examples to look at this. Suppose that you are computing a regression. You use a neural network to try to approximate some continuous function. In that case, we do not want the output to be artificially bound by some function like the sigmoid or the hyperbolic tangent, or only have positive values or something like that. So in this case, if you're doing a regression, the output neuron of your network should not have an activation function. Basically, the output is just a linear combination of the last hidden layer. And if you need to transform things more, just add more hidden layers in any way you want. Note that this is actually what happens with that theoretical network that we have in the approximation theorem, which is just as long as we have a linear combination of a sufficient number of neurons, then we can approximate any function. So in this case, the output is just a linear combination of the outputs of the last hidden layer in your network. If you want to do binary classification, then the sigmoid activation is a very good choice because it outputs values between 0 and 1, and this can represent, you can interpret this as the probability of belonging to class 1. And if you interpret this in that way, you can use the appropriate loss function to adjust your network to give you that probability, and then you actually have an estimate of a probability of belonging to a class. Sigmoid outputs is also good for multi-label classification. Multi-label classification is a problem where each example can belong to more than one different group. And what you want to do is to predict all the groups the example belongs to. So they are not mutually exclusive. In that case, you can use one sigmoid output for each of the labels, and then each of these will give you the probability that this label should be associated with that example. So this is another application for sigmoid output in multi-label classification. We also have multi-class classification. This is different in that we are assuming that each example only belongs to one of several classes. So it cannot belong to more than one. It belongs to exactly one of those classes. In that case, we can use softmax. Softmax has this general formula where you use the exponent e raised to so you take a vector with let's say the net value for each neuron, where you have a linear combination of the inputs or something like that. So you take some values are higher and other lower, it doesn't matter which, but they are all between you take all those different values, and then you convert this into a vector where all the values are between 0 and 1, and the sum of the values are 1. So when you output using the softmax, you output also a vector of values taken from the previous layers, whatever the values were there in the input, but the output is guaranteed to give you a probability distribution of belonging to one of the classes, because the sum of all these values are 1, So it must belong to one of the classes, and each value is between 0 and 1 and gives you the probability for that class. So this is good for multiple class classification because you can have, for example, 0, 0, 1, 0, and you know that it's telling you the probability is 1 of belonging to the third class and 0 of belonging to any of the others. Or you can have something that is closer, more indefinite, so you can have closer probabilities, and your classifier is telling you that it cannot decide very well between the different classes. So this is basically a generalization of the logistic function, like we use the sigmoid here, but this one is only for computing the probability of belonging to a class or not, or in this case having a label or not having that label. So each of these is a value between 0 and 1, whereas in softmax the sum of all the values adds up to 1, and then this probability is distributed between all the different classes. So these are some examples of the activations at the output layer that we can use for different problems. And now we can see what impact this has on the loss functions that we should use. Let's look first at this idea of what we're trying to do. So we have basically a set of data. In supervised learning, we have a set of labeled data, and we want to approximate some function. This is an unknown function that would map any example to some output. For example, the category, the class the example belongs to in a classifier, or some continuous value in a regression, something like this. And what we want to do is to fit the parameters of our model to approximate this function. For example, in a linear regression, we can adjust the parameters so that our line can change. But the question now is how we can find the best parameters. How can we decide that one line here is better than another so that we can adjust the parameters to find the best line? And for that, we can assume some things about what our model is telling us. So some way which we are interpreting our results or modeling what is happening, and then try to maximize the probability that our model is going to give us the correct data, or the data with the same kind of structure distribution that we are seeing in our sample. So let's suppose, for example, for the linear regression, we assume that the values that we have here on these points, the y values, are given by some unknown function plus some noise. And we assume that this noise is normally distributed. So there is something in nature that determines the relation between x and the point, but this is also affected by some random noise here. So we are going to try to approximate this unknown function, which is our model here. It's the straight line where we are adjusting the parameters to tell us the inclination, the position of the line, and so on. And we're going to use this line to try to approximate that function, but we know that there is some error associated here with the value of each point. So the probability of having some y value given this x, so if we give the coordinates here, the probability of having this value exactly there would be given by our function, but also affected by this error. So we can consider that to be something that is normally distributed around the prediction for our function, if our function is approximating the real one that is creating this relation between the values. So we can convert this into the joint probability here, the probability of the points extracting at random from nature one point with a given x value and this particular y value, the corresponding y value. We can write this probability as a combination of the conditional probability that we find here that we're trying to predict. That is the probability of having that y value if it has the x that we are observing, multiplied by the marginal probability of drawing that x from some distribution. So this would be the probability of the data given the parameters of our model, and this is also called the likelihood of the parameters of our model. And this is basically what we want to maximize. We want to find the straight line in this case, for which, if we consider that this data is distributed in a straight line plus some random noise, we want the straight line that maximizes the probability of finding this data. And this would be the maximum likelihood solution. And if we now do the derivation here, so basically to maximize the likelihood, we can ignore this marginal part here, because this will not depend on our parameters. We can also take the logarithm. Instead of doing all the products of the probabilities for all the data points, we can add the logarithms of all of those. And now we also know that the probability of having some value depending as a function, or given that we know the features of that point, is given by our prediction affected by some random error. Note that this is what we are assuming about our model, that we are predicting the right value plus or minus some normal distributed error. And if we replace everything here and we simplify the expression with the logarithms and so on, we end up having this loss function here. So the maximum likelihood solution, that is the line that will give us the largest probability estimate of having the points distributed like the ones we have in our training data, corresponds to the line that minimizes the sum of the quadratic difference between the predictions and the actual values that we have in our labels. So in this case, the maximum likelihood solution for a linear regression, when we assume in our model that we are trying to predict the actual value plus or minus some error that is normally distributed, if we assume this, then we reach this loss function that we need to minimize to adjust our parameters. So this is just one particular example, but the main message here is that this maximum likelihood approach, which intuitively is to obtain the parameters that maximize the probability of our data being as it is, will give us some loss function depending on what we are assuming about the model. So in this case, it will be the minimization of the quadratic error. Sometimes you can see this written with this 1/2 in the literature just because of the computation of the derivative, but basically it's minimizing the sum of the squared errors. But in other cases, we can have different loss functions. But once we reach here, this point, we have the loss function for training our model, then we just do the gradient descent thing, backpropagation and so on, and we can find the parameters. So the important part is getting a loss function that we can then use to optimize our parameters. So let's see this maximum likelihood approach more in general. We saw this particular example for linear regression, but in general, if we have a set of data points, our training set, that was drawn randomly from the universe, some population, and it was drawn with some probability distribution. We don't know this explicitly, but there is a structure in the way that our data is that is determined by this probability distribution with which we are drawing our sample at random. Now, we also have a family of probability distributions that is given by our model. For example, in linear regression, we had these probabilities of having some particular value y associated with x that was given by this normal distribution around the predictions of our approximation. So basically, we have in our model some way of estimating these probabilities for the data, depending on how we adjust the parameters. So this is a family of probability distributions, and each one is instantiated when we instantiate the parameters of our model. Now, we want to find the maximum likelihood estimates for our parameters, and this is basically the parameters that correspond to the maximum probability given by our model for the data that we have. Note that this data was drawn from the universe with some probability distribution, and so our estimates will also depend on that. We have this data and not some other data set that is completely different. So because of the problems of underflow and so on, we can simplify this, and we can convert this expression. Instead of maximizing the product of all these probabilities, we maximize the sum of the logarithms. So this is the same thing we saw before, and this is a standard approach here. And we can also rescale this. So instead of considering the sum of the logarithm of the probabilities for all our training data, we can consider the average. We just divide this by the number of points. So basically what we are saying is that we are trying to find the parameters for our models that maximize the expected logarithm of the probability of our model with those parameters that are the model with those parameters gives from some particular x, when x is drawn from the universe with the same probability distribution with which our data was drawn. So basically, if we keep resampling the universe in exactly the same way, and we find on average what the probability our model is giving for all those examples, this is what we want to maximize. We want our model to estimate the highest probability possible over this distribution. And intuitively, since we are drawing with this probability distribution from the universe, so the distribution with which the data itself is coming, we want basically our model to fit as best as possible that particular distribution. If our model gives us something that is very different from what we're seeing on the data, then this would be a lower likelihood case. We can see this a bit more formally by considering, for example, the Kullback-Leibler divergence. This is a measure of how two distributions differ, and so we can do this for comparing the distribution of probabilities with which the universe is giving us our data. So this is something we do not know, but when we collect data, it's coming with some probability distribution. And this is the probability distribution that our model, when we instantiate with some specific parameters and we have a specific hypothesis, this is the probability distribution it's giving us for the same data. Now, if we compare these two, then we can also see that regardless of what the parameters are for our model, this part of the expression is constant, because the way the data is distributed and the universe is giving us the data does not depend on the parameters of the model. Only the estimate given by the model is dependent on the parameters of the model. So if we consider this to be a measure of the divergence between what our model is estimating and what the data and the way the data is actually distributed, we can see that trying to minimize this divergence is the same thing as trying to maximize this term here. Because this one is constant and this one has a minus sign, so we can just ignore this part and try to maximize this. So basically the idea here is that maximizing the likelihood, that is maximizing the probability estimated by our model for the training data, is the same as minimizing the divergence between the probability distribution of the actual data, how we are drawing the data from the universe, and the probability distribution that our model is estimating. And note that this is something that is generic. It's not particular to a specific linear regression, classification, whatever. This is a general issue. We're trying to find the maximum likelihood solution. Is that intuitively or fundamentally, we are trying to make it so that the probability distribution our model is expressing fits as close as possible to the distribution the universe is giving us the data with. So now let's see what this corresponds in practice when we are trying to find a loss function and train our model. So basically minimizing the Kullback-Leibler divergence when we have one term here that is independent of our parameters ends up being the same as minimizing the cross entropy for our data. And so basically sometimes you're going to see this as a cross entropy loss function. But note that this term, cross entropy loss function, is a generic term that can refer to different functions, because depending on what our model is, the activation functions and so on, the actual result of this may be different from case to case. So let's suppose in supervised learning, for example, we are trying to predict a label based on the features. So our model is telling us something like this: the conditional probability of belonging to some class depending on the features and the parameters of the model. And what we are trying to do in the maximum likelihood solution is trying to maximize this probability for the data that we have. So given that distribution of points that we have in our training set. But this can be applied to the general case of different problems, in all these kinds of problems where we want our model to fit the data as well as possible. So in linear regression, we assume this, that we were predicting this continuous value from the features, and this was a normal distribution around our prediction. So this was the probability distribution we were considering for our model. And when we applied this maximum likelihood, that is to say, minimizing the Kullback-Leibler divergence between the distribution our model is telling us and the distribution of points in our data, which ends up being the same in that case as minimizing the cross entropy, we reached this particular expression. So this is one example of maximum likelihood, cross entropy, and so on. They tend to be all synonymous in this context, and this is what we get as the result. But if we do something different, for example, suppose we have a sigmoid activation function, and we are predicting the probability in a binary classification. In that case, the probability will be given by the product of the value on the output if the point belongs to class 1, or 1 minus the output if the point belongs to class 0, because the probability of belonging to class 0 is 1 minus the probability of belonging to class 1. And in that case, when we take the logarithms and so on and do exactly the same thing, we reach this logistic loss function. So note that for linear regression, the cross entropy loss function is the quadratic error, the one that we are trying to minimize. In this kind of prediction, for example, logistic regression, or if you have a neural network with a sigmoid output to predict the probability in a binary classification, what you get, the cross entropy loss function at the end, is the logistic loss function like this. So this is another example where the same approach, the same basic idea, will give you a different loss function. And moving on, if we want to find a loss function for binary classification for regression, we already saw. If we want to find for a classification with multi-classes, we can use the softmax activation, and then the loss function will be the softmax cross entropy, which is given by this expression here. So basically, what I want to transmit as a message here is that the core idea is always the same. We want to maximize the likelihood, which is to say we want the probability distribution given by our model to fit as close as possible the probability distribution with which we are getting the data. So our model is going to give us to approximate the data as well as possible. But when we do that, depending on what we are assuming about these probabilities, the way we are interpreting the model, and that includes the output function of the neural network, we will get different loss functions. So this means that when you are in practice designing your neural network and training your neural network, you need to be careful about which loss function you're going to use depending on the model and the output of the network. So if you're doing regression, if you're trying to predict a continuous value, you should have a linear output, do not have an activation function on the output neuron, and you should use the mean squared error in this case, because this is the loss function that corresponds to the maximum likelihood solution if you assume that your predictions are being affected by a normally distributed error. If you are doing binary classification and you are interpreting the result of your model as a probability of belonging to class 1, in that case you should use a sigmoid output. This sigmoid output will give you a value between 0 and 1, and this is the probability of belonging to class 1. But then you should use the logistic loss function, because this is the one that corresponds to the maximum likelihood solution when we assume that our model is giving the probability of belonging to class 1. And also for multi-class classification, if you can use the softmax activation function, which will return a vector of values between 0 and 1 such that they all add up to 1. And then you can use the softmax cross entropy, because this is the one that corresponds to the maximum likelihood solution when we interpret those values as giving us the probability of belonging to each class. Okay, so this is the important part. When selecting the activation function on the output of your network, be careful to think about what your network is trying to capture, trying to model, and then fit that with the corresponding loss function. There are some cases where things might actually work. For example, you can do binary classification with the mean squared error loss function and often get approximately the same results. It's not as efficient, but you can do it. In some cases, it will really ruin the results. For example, if you try to do regression with the logistic loss function, you probably will get overflows and errors in computing the logarithms and so on, because it will not make sense in this case, not even fit mathematically. So remember to think about the activation function and the corresponding loss function when creating your models. So to sum up, we saw this difference and some pros and cons of using wide, shallow models versus deep models. And the reason for this is that in theory, we can approximate any function with a very wide neural network with only a single layer. But in practice, we get advantages in stacking layers. So not only can we get the same shattering power with fewer neurons, but then we can have better representations of the features and things like that, better generalization and so on. So we saw then this problem of vanishing gradients that occurs when we have very deep models, and how the rectified linear units and variants can help us solve it. And then, so basically for hidden layers, we use this type of units, but then for output layers, it depends on what problem you're trying to solve. And here you will also have to think about which loss functions to use, because they should correspond to the assumptions you're doing about the model and the kind of activation functions you have on the output layers. So you can see more about this in these chapters of Goodfellow, and if you and you should take a look at the documentation on the activation functions in TensorFlow. This will give you an idea of the kinds of activation functions that are already implemented and that you can choose. So let's take a short break. We continue at 10 minutes after 5, okay? In about 6 minutes. See you soon.